Welcome to Are You Chemistry GCSE Ready? This playlist takes you through loads of example questions and guided solutions for every single topic in your chemistry GCSE. So it's a perfect way for you to test your chemistry knowledge. If you feel like you need a quick review or you just want the ideal revision companion for these videos, then make sure to download my free chemistry GCSE revision notes. I've linked them in the description below. Or if you're ready, let's dive straight in.
So gas volumes. First question here, how do we calculate the volume of gas from its number of moles? So remember, we essentially have this triangle, these two triangles here, where you have your volume at the top and then 24 moles on the bottom if your volume is in decimeters cubed, or if your volume is in centimeters cubed, then you have this 24,000 on the bottom. And remember, from all of our work before about concentration, you should know that that is because there are 1,000 centimeters cubed in a decimeter cubed. Okay, and what this triangle, this equation is essentially telling us is that in 1 mole of gas, that takes up a volume of 24 decimeters cubed if you're at atmospheric pressure and at room temperature. So does the volume of gas depend on the chemical makeup of the gas? For example, does carbon dioxide take up more or less space than nitrogen gas? The answer is very firmly no. They take up the same volume. It doesn't matter what gas it is, 1 mole of it, as long as we're at atmospheric pressure and we're at room temperature, will take up a volume of 24 decimeters cubed. And the reason for that is, you might think, but surely some molecules of gas are larger than others, don't they take up more space? Remember that all of your gas particles are so extremely small compared to the amount of space between them. So it's kind of why it's negligible or irrelevant what the makeup of your gas is. What's much more important is the amount of space that exists between those different gas particles. Which makes it very handy for calculations. So for all gases, I can say that 1 mole of them takes up 24 decimeters cubed in volume. So let's do some conversions. What mass will 6 decimeters cubed of nitrogen gas have? And it gives me my relative atomic mass of nitrogen being 14. So with any kind of conversion like this, my first thought is I need to first figure out the number of moles, because remember, that's what gets included in this equation that relates the number of moles to the volume of my gas. Then I can work out the mass from there. So how do I work out the number of moles that I have? Well, I've been told the volume, and as I just said, we can relate that to the number of moles by doing volume divided by 24 is 0.25. Remember, that's 24 here because it's in decimeters cubed, but had that volume been given to me in centimeters cubed, then it would have been divided by 24,000. Anyway, I've got 0.25 moles of nitrogen gas. Now I need to work out what mass that is, and in order to do that, I need to think about my equation that relates mass to number of moles of a substance, and it's figuring out my relative formula mass. I need an extra piece of knowledge here, which is to know that my nitrogen is a diatomic molecule, which means that there are 2 nitrogens that are bonded together. So 14 times 2 is 28. That is my relative formula mass. And then if I have 0.25 moles of them, I have 0.25 times 28 is 7 grams in total here of nitrogen gas. Okay, potassium nitrate decomposes on heating to form oxygen gas, nitrogen dioxide gas, and potassium oxide. What is the total volume of gas produced when 101 grams of potassium nitrate reacts? I need to give my answer in decimeters cubed to 3 sig figs, and I've been given some relative atomic masses. So let's have a look at this equation first. So what I can see on my left-hand side here is my potassium nitrate. And then on my right-hand side, that produces this solid, potassium oxide, and then these 2 gases, nitrogen dioxide gas and oxygen gas as well. So I'm going to need to work out the volume of both of those gases and then add it together to give my total volume of gas produced. Let me get my table ready then. And I've just scribbled out that column there for my potassium oxide because it's not going to be involved in my calculations. So let me put in some ratios here first so I can see 4. I'm using the big numbers in big factors in front of my various things here. So 4 for my potassium nitrate, 4 for my nitrogen dioxide gas, and 1 for potassium oxide. That's the ratio in which these things are produced. And then the other piece of information I have is that I have 101 grams of my potassium nitrate to start with. So what I need to do, again, I'm going to need to figure out how many moles that is of potassium nitrate, because that will be what I use and the ratios to figure out how many moles I get of these other two gases. So in order to do that, I need the relative formula mass first of my potassium nitrate. So I've got 39, my relative atomic mass of potassium, plus 14, the relative atomic mass of nitrogen, plus, and then 3 oxygens there, so 16 times 3. And if I add those all together, I get 101. Now to figure out the number of moles that is, I take, remember, my mass, divide through by my relative formula mass, and that tells me the number of moles. So 101 divided by 100 equals 1 mole of this potassium nitrate. And then I can think about the following. If I had 4 moles of potassium nitrate, that would produce 4 moles of nitrogen dioxide. But I don't have 4, I only have 1. So these are in the same ratio to each other. So if I have 1 mole of potassium nitrate, then I will get 1 mole of this nitrogen dioxide gas. But then for my oxygen, when I had 4 moles of potassium nitrate, that only made 1 mole of oxygen. So actually, when I only have 1 mole of potassium nitrate, that will make 1/4 of a mole of oxygen. And now I've got the number of moles for both of my gases, then I need to remember what volume does that number of moles of gas take up. And that's when I remember in my head what I need to do is the number of moles multiplied by 24, because it's asked for my volume in decimeters cubed, to get the volume. So I've got 1 times 24 there for my nitrogen dioxide gas, and then I've got 1/4 of a mole times 24 there for my oxygen, and that gives me 24 plus 6 is 30 decimeters cubed.
Just before we go into the tips and tricks section, if you do want some extra advice to getting that grade 9 for your GCSE, then why not download my free 20-minute exam success guide? Just click on the link in the description below. I'm going to give away all of my best advice and secrets, and completely for free, so why not?
So make sure you're very confident on converting from one unit to the other. That could be mass to moles, but also remember for your volumes, decimeters cubed into centimeters cubed as well. You need to be able to do these quite quickly and confidently in various calculations without your exam. Secondly, since every gas occupies the same volume for the same number of moles, this means that the reacting gas calculations can be quite simplified. You saw that final step there. Once you've figured out the number of moles of each gas, actually it's very quick to figure out how much volume that's taking up. That said, converting volume to moles first is usually the safest option. If you're stuck in the exam, make sure you try and get some of the marks here. So just calculate moles of each substance and then just move on to the next question if you really struggle with these calculations. But you can always pick up some marks for doing that step first.